All right, so we didn't spend much time on the linear idea of mass because it's fairly intuitive. You guys know bigger things, heavier things tend to resist motion more. Rotational inertia is the angular version of mass, and it's a little bit more complicated and a little bit more involved than regular mass was. So the first way to talk about it, and this is you'll probably see this if you go anywhere else online talking about rotational inertia, is to just imagine a stick and you have a mass that you can put at different places on the stick while you try and rotate it. So I kind of just have this idea. I should have grabbed something better than a pen, but imagine that this is the stick and I'm trying to rotate it. And I can either put the mass here at the bottom, halfway up, or all the way at the top. If you think about it, which one of those would be the hardest to kind of move back and forth quickly? Because that's a good way to think about which one of them is going to be resisting the angular acceleration the most. And I'm sure you guys can visualize it. And if you can't, go ahead and try it out. Grab one of those rulers and tape some of the washers to it at the base, halfway up, and all the way at the tip. And we'll find that uh, the farther the mass, there. The farther the mass is from the pivot, the more it's going to resist. So that works if you're doing it upright. The other version I had is kind of like if you're holding it sideways and you have whatever it is, and you could either have the mass really close to your hand where the pivot is, further out, or even at the ends. And we know if we're doing it with this second version here, that it's not an issue of torque because the torques would be equal on each side as you're moving it back and forth. So it's not like the force of gravity is resisting you there. It's really an issue of the mass resisting you. So there's two pieces to this. The first piece that we've already talked about is the position of the mass. And the other one, which is a little bit more obvious, is the mass part. That if just the mass itself gets bigger, then it would also resist it more. So the equation, the general equation that describes rotational inertia is going to be I equals some constant value depending on the shape times mr squared. So this is the general form for it. And then we can think about different shapes then have different rotational inertias. So this little picture that I have here with the ring, the disk, and the sphere is a classic experiment that we could do in the classroom if we were in the classroom right now. And if we rolled a ring, a disk, and a sphere down a hill, the sphere would get to the bottom first, then the disk would get there, then the ring would get there. And that works pretty much no matter how we set that up. But the classic way to do it is to use items so that the mass and the radii of all three of those objects are exactly the same. So the only thing that they have that's not in common is their shapes, which then goes to the relationship between those the distributions of mass. So if you think about it, a ring has all the mass really far outside. It's at the very edges of the ring, which means it would have a really high rotational inertia because rotational inertia is really all about the distribution of mass. A disk on the other side has it a little bit more spread out because it's all the way across the disk, but a sphere actually has it the most spread out. And the reason why the sphere is the most spread out is because not only does it spread all the way in one dimension, it also spreads out like this way, and you have more of the mass at the center of rotation. So because the rotational inertia for the sphere is the lowest, it's going to resist rolling down the hill the least, and therefore be able to speed up the fastest. So one of the key ideas, in addition to this statement here, the farther the mass is, we want to just say rotational inertia Rotational inertia is all about the distribution of mass from the center of rotation. So the more mass we have and the further it is from the center of rotation, the more rotational inertia we'll have. Now, the formula for rotational inertia isn't actually something you guys are expected to know. The idea that it's about mass and distribution is expected, but if you were asked to solve a problem, you would either be finding the rotational inertia by solving for it in another equation, or they would give you specifically the equation for the shape that you're dealing with. So for example, if we're dealing with a point mass rotating around a center of mass, a point mass would be like an infinitesimal point that just has mass. So that's pretty ideal. But something like a planet going around the Earth, we can describe as being a point mass because like it's basically all of the mass exists in one location relative to how big it is from the center of rotation. So the rotational inertia for a point mass is just I equals mr squared. So where r is how far it is from the center of rotation and m is the mass of the object. For a rod, the rotational inertia formula is one third. Yeah, is that right? Yeah, 1/3 mr squared. Once again, m is the mass of the rod, and then r is the length of the rod. So sometimes you'll see it as 1/3 ml squared, but I'm just using r for all of these. That's if the rod is rotated um, from uh, from the end. So if I'm rotating it here and doing this, that would be 1/3 mr squared. There's a different equation if you rotate it from the middle or like other points along the line. And then, of course, there's a different rotational inertia if you rotate it on an axis that goes through the entire rod, although the rotational inertia there would be pretty close to zero. Then for a ring, the rotational inertia is actually the same as a point mass. And the reason for that is actually a little bit interesting because if you imagine that point mass, but then you spread it all the way around a disk, it's still all effectively the same distance from the center of mass. So it's effectively the same as a point mass or a ring. A disk, on the other hand, has a rotational inertia of 1/2 mr squared, and a sphere has a rotational inertia of 2/5 mr squared. So if you were ever asked to solve a problem and you needed the rotational inertia to solve it, the value would be given to you, or they would say, here's the equation, here's the mass, here's the radius, now figure it out from here. So I have one example problem that helps us with learn one more important thing about rotational inertia, where I have a rod with a ring or with a disc with a point mass on the end, like some heavy mass just attached to the very end. So my goal is going to be to find the rotational inertia of the whole thing. And I don't have anywhere on my rotational inertia formulas the point mass slash rod formula. But rotational inertias are additive. So I can just add up the different pieces. I can add the rotational inertia of the rod plus the rotational inertia of my point mass, and that's going to give it to me. So the formula for a rod is right here, 1/3 mr squared. I'm going to have to use the mass of the rod there, plus, and then the mass of a point mass, or the inertia of a point mass is m. This is going to be for the point mass, r squared. The r is the same because the point mass is 1 meter away and the length of the rod is 1 meter. So then I'm just going to go 1/2. The mass of the rod is 0.5 times 1 squared plus 1 times 1 squared again. And let's see, that's going to be 1 1/4, so 5/4. And then the units of rotational inertia are kilogram meter squared. So that's how you'd find the rotational inertia of a combined system. So just be aware that you can just add them together once you have the formulas for the individual pieces. All right, so that's the intro to rotational inertia. We'll be doing a little bit more with it, but it is one of the more challenging concepts in this unit. So we'll do quite a few videos and discussions in class on this.